All right, let's talk about system design. You ever click a button on a website like Buy Now and just wonder, how does that even work so fast? Well, today we're going to follow the incredible hidden journey of that single click to really understand the machinery that powers the modern internet. So there you are. You found the perfect thing, you hit that button, and bam, it's done. It feels like magic, doesn't it? But behind that simple click, there's this lightning fast, totally invisible chain reaction happening. So what exactly is going on in those few milliseconds? Let's trace the path. Okay, so the journey begins. The very first hurdle is a simple one. How does your computer find the right server to talk to? I mean, the internet is just massive. It's got millions and millions of servers. How in the world does your browser know exactly which one to send your request to? Well, at its very core, pretty much every website you use is built on this one simple idea. You've got a client, that's your web browser, and it sends out a request. And somewhere out there, a server, which is just a powerful computer, is listening for that request. It processes it and then sends a response back. It's this constant back and forth, this conversation, that is the fundamental heartbeat of the entire web. But how does your client find that specific server in the first place? Well, every single device connected to the internet gets a unique IP address. You can think of it just like a phone number for a computer. But let's be real. You're not going to remember a string of numbers like 172.217.168.238. That's not very friendly, is it? We need a better system. And that is exactly where DNS comes into play. DNS is literally the internet's phone book. It's brilliant. When you type in a nice, friendly website name, your computer just asks a DNS server, hey, what's the IP address for this name? The DNS server looks it up, gives your computer the number, and just like that, your browser can make the call. Connection made. So, connection established. Your browser has found the right server. But what now? They can't just start yelling data at each other. They need a shared language, a set of rules to make sure the conversation is orderly and makes sense. Let's look at how that works. That shared language is called HTTP. But almost everywhere you look today, you'll see HTTPS. And that S, that little letter, is a huge deal. It stands for secure. It means that all the data flying back and forth between your browser and the server is encrypted. Thanks to something called SSL/TLS, it's all put into a secure private tunnel, so even if someone managed to intercept it, it would just look like complete gibberish. Now, what's really fascinating is how we structure that communication. This is where an API comes in. The best analogy is a waiter at a restaurant. You, the client, are given a menu, that's the API, that tells you exactly what you can order and how to ask for it. You make a structured request, the waiter takes it to the kitchen, that's the server, and the kitchen prepares your order and sends it back. It's the formal contract for how these two systems agree to talk. And just like you've got different kinds of restaurants, you have different styles of APIs. REST is the classic, most common style. It's very structured. With REST, it's kind of like ordering your main course and then having to call the waiter back to order a side dish, two separate requests. GraphQL, on the other hand, is much more flexible. It lets you give your entire detailed order all at once. I want the user, their last 3 posts, and the comments on those posts, all in one single, efficient trip. This can be a massive game changer, especially for mobile apps on slower networks. So our system is working beautifully for one person. But what happens when you get popular? When that good problem hits, and suddenly thousands or even millions of requests are flooding your server all at once. That one little server just can't handle that kind of crowd. So how do we scale up? Well, you've got 2 main options. The first is vertical scaling, or scaling up. This is like swapping out your server for a bigger, beefier one. More CPU, more memory. It's simple, but you eventually hit a wall, both in terms of cost and physical limits. The real secret to massive scale is horizontal scaling, or scaling out. Instead of one giant super server, we just add more and more regular servers to our fleet, letting them share the work. Okay, but if we have a whole fleet of servers, how does any given request know which one to go to? This, right here, is one of the biggest aha moments in system design. We put a load balancer in front of everything. It acts like a brilliant traffic cop. It sees all the incoming requests and intelligently distributes them across our healthy servers. And the best part? If one of those servers goes down, the load balancer just stops sending traffic its way. It's the key to both amazing performance and incredible reliability. So our request has been expertly guided by the load balancer to a healthy server. Awesome. Now, what is that server supposed to do? Well, most of the time, it needs to deal with data, either saving new information or pulling up something that's already there. So where does all that data actually live, and how do we get it fast? This is the job of the database, the system's long-term memory. And broadly speaking, we have two main flavors. SQL databases are like meticulously organized filing cabinets. Everything has a very specific place and follows strict rules. This is absolutely perfect for things like bank transactions, where you can't afford any mistakes. Then you have NoSQL databases. These are more like a giant box of flexible folders. They're designed for huge scale and can handle all sorts of different data, which is great for something like a social media platform. The choice between them really depends on what your application needs to do. Now, here's the thing. No matter how fast your database is, getting data from a spinning disk is always going to be slower than getting it from a computer's main memory. So we add a secret weapon, a cache. A cache is just a small, super fast layer of memory where we keep copies of the data we use most often. It's like the system's short-term memory, and it makes everything feel incredibly snappy. And here's how that works. When the application needs some data, the very first place it looks is the cache. If the data is there, we call that a cache hit. Boom, it's returned instantly. Super, super fast. If it's not there, a cache miss, no big deal. The application just goes to the slower database to get it. But, and this is the clever part, on its way back, it saves a copy in the cache. So the next time anyone asks for that same piece of data, it'll be a lightning-fast cache hit. But what if so many people are trying to read data that even our main database starts to get overwhelmed? Well, we can scale the database too. With replication, we create read-only copies of our primary database. All the new stuff gets written to the main one, but the thousands and thousands of read requests can be spread out across all the copies. It's just like a library having multiple copies of a super popular book so lots of people can read it at the same time without having to wait in line. You know, as our application grows, it's not just about adding more servers. The actual structure of our code, the way we've built the software, needs to evolve too. An architecture that works great for a small startup can become a huge bottleneck for a big company. Let's see how that unfolds. A lot of applications start out as a monolith. Think of it as one giant building where every department is just crammed into one huge, messy room. It's simple to start, but after a while, if you want to change one thing, you risk messing everything else up. The modern approach is microservices. This is like giving each department its own separate building. You have a service for users, a service for payments, a service for sending notifications, and each one can be developed, updated, and scaled all by itself. So how do all these separate little services talk to each other without causing chaos? What if the payment service needs to tell the notification service to send a receipt, but the notification service is busy? This is where a message queue is brilliant. It's like an internal post office. The payment service just drops off a message that says, send receipt to user 123 into a mailbox. The notification service can then pick up that message and handle it whenever it has a free moment. This makes the whole system so much more resilient. Wow, okay, let's just step back and recap this incredible trip we've been on. Our request started with DNS to find the server's real address. It then used an API to have a structured conversation. A load balancer acted as a traffic cop to direct it to a healthy server. That server then used a fast cache and a reliable database to get the job done. And the whole thing was built on independent microservices to handle all that complexity. So we've designed this amazing system that can scale to handle millions of users. That's fantastic. But all this complexity brings up a whole new set of really tough questions. What happens when one of those hundreds of little microservices fails? Or when a database copy goes offline? Building a system that's not just big, but also truly reliable and can handle failure, well, that's the next great challenge in the journey of system design.